today's lecture. What I wanted to cover and talk about, well, first, any questions? Maybe I should go for there. Okay. So I wanted to talk about today was some aspects of public key cryptography. And hopefully everybody can see the slides okay. So as I mentioned before, one of the main challenges with public key cryptography is how do we, or cryptography with private keys was exchanging the key. Okay, somebody, yeah, please mute. There we go. How do we get the sender and receiver to agree on a secret key without anyone else finding out what is that secret key? Anyone who accepts can intercept a key in transmission. If they get the key, they're able to read it. They could later modify, forge all messages, and nobody would know the difference. So with key management, let's see if, what we want to worry about is the generation, transmission, storage of keys. I've talked about this. All keys in our secret key crypto system must remain secret. Secret key crypto system often has problems with secure key management with large numbers of users because there's just a lot to deal with there. So to solve this problem, Whitfield Diffie and Martin Hellman introduced the concept of public key cryptography in 1976. So this was the first public key crypto system. Excuse me. It was used in a number of commercial It's used in a number of commercial products currently. It's a practical method for exchanging secret keys securely that can be used for subsequent encryption of messages. And the security relies completely on the difficulty of computing discrete logarithms. For some reason, I got to ask, did I cover that? I didn't cover this material already, right? Or did I? This is looking like I just said this. Maybe I covered it in another class. No, nobody's saying anything? Chat? I talked about Diffie-Hellman a little bit, not much. Okay. Okay. I think I may have duplicated some of the slides slightly somewhere. So when we talk about communication with encryption, we often have several users, or what we call parties in the communication. You're a mathematician, you write them down, you give them names, you give them labels, A, B, C, D. The power of mathematics is when you're defining things, you always give them names, give them labels to use them. So let's make it a little more fun now. And this is what the crypto community does. We have Alice and Bob, A and B. These are the two parties that wish to communicate with each other. Alice and Bob love to talk, but they want to talk secretly. Charlie and Trent are often trusted third parties who help in that communication. T for trust, Charlie for certificate authority is usually where it comes from, but Charlie and Trent's fine. Eve is jealous of Alice and Bob. She tries to eavesdrop on their communication to hear what's going on, to see, what are they chatting about. And last but not least, we have Darth and Igor, the evil intruders or people who want to do more than just eavesdrop. They want to do some nasty things. All right. So here's an example. We want Alice and Bob to be able to communicate secretly. We want Alice and Bob to be able to exchange information so that they can create a secret key that they can use for, say, a DES algorithm or AES algorithm and communicate back and forth. All right. So first, Alice and Bob agree to share a public key. They agree on two large prime numbers, N and G. These are publicly known. N should be a prime number, so not divisible by any other number other than 1 in itself. It should be large, at least 512 bits in length, preferably 1024. G needs to be between 1 and N, and G should be a primitive root of N. Now, what do I mean by primitive root? A primitive root of a prime number is a number whose power successfully generate all the elements mod Q. Okay, so what do I mean by this? Let's look at an example. All right, let's say 7 is my prime number, my quote-unquote large prime number. I'm not going to show you a real 512-bit prime number and do math with it because it would take up too much of the screen. So 3 is going to be another number, right? So 3 to the first power is 3, right? And what I'm going to do is just write this as 3 to the 0 times 3, so, which is a 1. 1 times 3 equals 3. 3 mod 7. 3 squared is 9, which is 3 to the first mod 3, which is 3 times 3. That's 9. That's 2 mod 7. 3 to the 9th is 27, which is 3 squared times 3. Now, what's interesting is we know 3 squared is already, because of this previous line, 2 mod 7. So we can rewrite 3 squared as 2. This simplifies our math. 2 times 3 is 6. 6 mod 7 is still 6. 3 to the 4th is 81, but it's also 3 cubed times 3. We know 3 cubed from the previous line is 6. 6 times 3 is 18. 18 mod 7 is 4, right? So if we look at the far right, and I can go up to 3 to the 7 here. So if I look at all of these numbers, mod 7, I get 3, 2, 6, 4, 5, 1, 3. If I look at this, notice 3 to the 7 here is also a 3. But if I look at the other ones, I get 1, 2, 3, 4, 5, 6. I get all the numbers from 1 to Q minus 1. What we call this is these are residues. These are the remainders, what's left over, so the residues. When we do modular 7 arithmetic. And look, I got all of them except for 0, and I can't get 7 because it's mod 7. So if I can get all of those, I've got a large sequence of these. So I want to do this. I want to have this n, or this value, I wrote a here, it should have left it as n, of 3, such that whatever number I pick here to do the exponentiation, I get a different number from 1 to Q minus 1. If I can do this, basically I've shuffled these numbers from 1 to 6 and gotten a different set of results here. So these are distinct and consist of the integers from 1 through Q minus 1. Now, not all, this doesn't always work, especially if Q isn't a prime, there's definitely some issues here. But we want to deal with as many of these as possible. And like I said, we want to be able to shuffle them. So the secret is going to be dealing with this capability. All right, so how do I do that? Okay, I just said this. So we want to use this capability of doing this math to help us generate some secret values. All right, Alice, we're a public key crypto. Alice needs some type of private key. They will choose a large random integer, we'll call it X. Bob needs a private key. Bob will choose a large random integer, call it Y. Alice will use their private key and the public numbers G to the X mod N. So G is this generator that is a primitive root of N. And they will take G, raise it to this little x, their secret value, mod N, and they get a capital X. Now, so if it was, given that example again, if it was, let's go back up. So say 4 was their secret value, or 3 is their secret value, they'll get a 6. So 3 cubed is a 9, mod 7 gives them a 6. Alice will send that 6 off to Bob. Alice will also communicate with Bob, agreeing on what these G and N are, but that's public, doesn't have to be private. X is private, capital X is sent to Bob. Bob uses their private key, doing the exact same thing, their Y, computing G to the Y mod N, sending capital Y to Alice. Alice then takes that capital Y they got from Bob, raises it to their secret value X, mod N, to get a K. Bob does the same thing, taking the value Alice sent, raising to the Y mod N, getting K2. Now, like I said, X is private, N is public, Y is from Bob, which was sent publicly over the internet, K1 is computed. How does this work? X, the public value from Alice, received by Bob, is raised to the power Y, the secret value of Bob. So Alice is public, Bob's private, mod N. Let's rewrite this. What Alice did was took Alice's private, G to the X mod N. So we're going to take that value to the Y mod N. If I do a little math, I can bring that Y in. That's G to the XY mod N. I can switch the order of these because it's just multiplication. I can bring that X back out. And this G to the Y mod N is just Bob's capital Y to the X mod N. So Y to the X mod N that Bob calculates is the same thing as X to the Y mod N. Y to the X mod N that Bob calculates is the same thing as X to the Y mod N that Alice calculated. So K1 equals K2. These are the identical keys. Okay, that's the math behind it, being able to do exponentiation. Now, why is it secure? It is secure for several different reasons. One, we have to remember N, X, Y, these are big numbers. So somebody can't just create a lookup table and say, oh, this capital X, well, that corresponds to that, lowercase x because I did this lookup table. Because if you got a 512-bit number, 2 to the 512, well, we don't have that many molecules in the galaxy. We're not going to store it anywhere and recover and keep track of that. So these are really big numbers. Okay, so example here with small numbers, if our common number, let's just look at this. Random number was 4, the common 2, so the primitive root, 2 to the 4 is 16. Here our random is 5. This is Bob's, this is Alice's. 2 to the 5 is 32. We switch them. And then you take that public, 32 to the 4, that's this number, or 16 to the 5, that's this number. They're the same. It's the same in normal arithmetic. It's the same in when you do modular arithmetic. And so this primitive root, G is our generator, is another word for it. I don't think I actually... Oh, that slide's missing. Okay. So this is the protocol, the key exchange protocol. We got Alice and Bob wanting to talk to each other. Same exact thing, just written slightly different, showing the details of it. So first I want to know, is there, Any questions about that? I'm not seeing any. Let's see. I'm trying to find this real quick. I had a, well, I'll get to it. All right. So like I said, how is it secure? The protocol depends on the ability to do what we call, discrete logarithm. Okay. It assumes that it is computationally infeasible to calculate the shared secret key. Even if an attacker obtains N, which they will, because that's public, G, again, because that's public, X and Y, they're just sent over the internet. They still believe the attacker cannot generate successfully the key K. Does that make sense? Any question on that? Okay.
I have a question.
Yes.
Should we be expecting like this math portion on a test or a quiz? Like, should we become like really familiar with it? Because I'm pretty confused, and I'm sure other people are.
Yeah. So there will be some homework. Test or quiz, it's going to be more generic. So what are you confused about? I can try again. I know it is tricky.
I think I'll just have to like look back over my notes because I'm just confused about the like the primitive root and the math that goes behind it. So
okay, that makes sense. I'm gonna get you more confused because I'm mean. So this is part of one of the Internet Engineering Task Force standards. So actually, I should scroll down just a little. Well, never mind. This group, this is the hex value of the prime. So this is a 1,536-bit group. The generator is 2. That's the nice thing. The generator is really simple. But in this group, and in the next group, group 2048 bits, the primes are really big numbers, and they calculate them using this. So this is 2 to the 248 minus 2 to the 194 minus 1 plus 2 to the 64 times 2 to the 19 pi. This is the square brackets, then round it to the nearest integer, plus 12.124476. That's just a way of writing the prime. So this is group 14, officially in the standard. This is its huge, huge, huge number. Now, for those of you who aren't familiar with hexadecimal values, I think I've talked about them briefly. This is base 16. So 1, 0, and base 16, this is instead of base 10 where the 1 is times 10, it's the 1 times 16. So 1, 0 is 16, 1, 1 would be 17. 2, 0 would then be 2 times 16 or 32. And because we have 16 possible digits in each location, we go 0 through 9, and then we list A, B, C, D, E, F. So this is just a different way of writing the numbers, but I could do FF. F, I like using FF as a great example. F here is 15. This F is 15 times 16. So that number's basically, it's 255. it's 00 through FF. There's 256 possible values. 00 being the first one, FF being the 255th one. 2 to the 8th. It's just a convenient way of writing this. We could write the FF. Each F is 4 ones in binary notation. That's 8 bits. So FF. And we do this because it's a really convenient way of wrapping around the binary numbers in a computing system and writing them. You don't have to know how to do that for this class. You do have to do it for other classes. But that said, you can tell that this is a big, big, big number. Okay, I'm just sharing this to say these standards are out there. And so Bob and Alice, when they want to communicate with each other, say, hey, let's communicate. They have a way of exchanging information. And basically they say, let's communicate using group 14. That's the public N and G that they're using. Then they share these values. Okay. So Alice picks a random number, takes that 2 in that group 14 she's using, raises it to this random number, modulo that really, really big prime, and we have a computer do the calculation, creates the value she wants to send to Bob. Bob goes the other way. And notice and I apologize for this, I got these slides from different people. Everybody switches X's and A's and Y's. It's the place that matters. She takes Bob's public value, raises it to her private value, mod Q, and they get the key. So just knowing you have this primitive number, this generator, you raise your private that generator to the private value mod Q. Okay. Like I said, it's hard because the attacker can't just take this Y. Whoops, where am I? Can't take these generated values and reverse this process, even knowing N and G. It's just really hard. Okay. The other thing the attacker can't do easily is take these two values, X and Y. Let me do this. For some reason, I don't have my drawing tablet today. Okay. Let's see if I can do this with this one. So X is G to the little x mod this prime N. It's hard to take that and this, G to little y mod N, and combine them in some way. If I tried to do math multiplication or anything with this, I could get G to the X times G to the Y, which is G to the X plus Y. So G to the X times G to the Y is G to the X plus Y. But Alice and Bob are using G to the X times Y. These are not the same. And because they're not the same, the attacker can't combine it that way. So and if the attacker tried to add these together, it wouldn't work. There's no way for the attacker to get this combination without knowing one of these values. It's computationally infeasible. That's the whole goal. So that should be enough for this class, for you to understand it's just really hard for the attacker. I told it to clear. There we go. The problem with this, which I'll come to in a second, is it's really good for exchanging secret keys. But you don't know who you're really talking to. I think Alice thinks Alice is talking to Bob, and Alice could be talking to Darth, could be talking to Eve, and not know, and get this value back claiming to be from Bob and do the calculation and think we're good. Also, it's good for exchanging keys, but it's not really good for just protecting confidentiality from receiving a secret message from a stranger or from anybody publicly which is what we wanted to do. So Revist, Ron Revist, I don't remember all the names. So Revist, Shamir, and Edelman. Ronald Revist, Adi Shamir, and Leonard Edelman said, hey, let's take this a step further. What we want to be able to do is send encrypted messages from sender to receiver, and the receiver can decrypt it and read it. Anybody else who receives it can't read it. Okay, so that's the idea. And we don't want to have to create this secret decryption key first. We don't want to have to do this key exchange. So it's a different way of solving the same problem. Whoops. And there's been a lot of work on this since, what, 1978. No serious flaws have been found. Now, I do want to mention the National Security Agency and the U.S. government, National Institute of Standard Technology, is no longer recommending this form of public key crypto. There's another one that's much more mathematically complex using what we call elliptic curves instead of discrete logarithms. But this still does work. It just requires more bits to be truly secure, because you can still break it if you have a really strong computing system. I said computationally infeasible. Difference is maybe it's not computationally infeasible for me, but not for a nation state with a supercomputer. All right. It is similar to how Diffie-Hellman works. We want to use two keys, D and E, for decryption and encryption. Plain text block P will be encrypted as we take that, instead of using just this generator that we use in Diffie-Hellman, we use their whole message, or whatever portion of your message you want, raise it to the power E mod n. We want the decryption so that this thing raised to the D now mod n will give us back the original. So the encryption key uses E and N, and the decryption key is D and N, because that makes sense. Encrypt, you need to know E and N. You can take the plain text and encrypt it. To decrypt, you take the ciphertext, D and N, the decryption key, and decipher it. I need to know D here to decipher, but I don't need to know E to encipher. I need E to encipher. I don't need to know D. So the goal is, can I find a pair E and D where this works, along with a number N, but they can't find one from the other. So they looked at the Diffie-Hellman approach and said, let's tweak it a little. Let's pick a value N. Now, N is not going to be a prime number anymore. N is going to be a product of two primes, P and Q. Both primes are very large numbers, so that N will be a large number. So like N could be 512 bits, P and Q would be close to 512 bits. And then we choose an integer E, relatively prime to what we call the Euler-Toician function of N, which is just these two numbers, P minus 1 times Q minus 1. Now notice this P minus 1. Remember when in the Diffie-Hellman, the primitive roots, there's P minus 1. There are P minus 1 values less than P. P minus 1 values here, they're relatively prime to P. There's Q minus 1 values relatively prime to Q. What do I mean by relatively prime? I should be careful. Relatively prime, they don't share a common divisor. So 4 and 8 are not relatively prime because they can both be divided by 2. 4 and 9 are relatively prime because their common divisor is only 1. 4 is 2 squared, 9 is 3 squared. So 2 doesn't divide 9 evenly, 3 doesn't divide 4 evenly. So being relatively prime to each other, they don't share a common divisor besides 1. So that's if you don't do that, you don't get this complete residue. You don't get all these other numbers and wrap around in that sequence like I showed you with Diffie-Hellman. That's the important thing to understand, is that they pick these numbers in a way to give them the biggest diversity of solutions. And then they find a second integer d such e times d mod this number p minus 1 times q minus 1 equals 1. Okay. I don't expect you to understand this math. I don't expect you to repeat this math. It's really cool. And there's lots of derivation and stuff you can do to show how this works. What you need to know is n is a product of two primes. And we can do this math with it. Now the user will take that public key E, this encryption key, and the product of two primes, and send them out to the public. Hey, this is my public key. And everybody will have a different N. Actually, everybody should have a different N. Now, what's the likelihood of them having a different N? Well, these numbers are very, very big. Likelihood of two people, what is it? There's, let's keep it simple. Let's say there's 8 trillion people in the world. What is that? Yeah, I'm not doing my math right. Let's see. 2 to the 10th is 1,000. So 2 to the 20th is 1,000,000. 2 to the 30th is 1,000,000,000. 2 to the 40th is 1,000,000,000,000. So 2 to the 43rd would be 8 trillion. I'm talking 2 to the 512. Whole lot bigger. So if everybody picks even 1,000 public keys, 1,000,000 public keys, it's going to be a very, very, very small fraction of these. Even if I picked 100, I picked a million public keys, so that's 2 to the 30th. I'm at, roughly 2 to the 72. There's still 2 to the 451 out of 2 to the 450 possibility. So it's just a huge, huge unlikelihood. All right. So even though n is known to be the product of two primes, if they're relatively large and they follow certain rules, it's not feasible to determine the primes p and q, and therefore not the private key d. Okay, that's the goal. Now what we're finding is, a 512-bit RSA key is about as strong as an 80-bit DES public key or private key in terms of how much time it takes to break it. But you go up to 1,024-bit or more in these public keys, it's fine. So let's talk about this just a little. How do we generate the public key and the private key? We pick 2 large prime numbers, P and Q. Again, for math simplicity, I'm going to pick 2 small ones, 7 and 19. N will be the product of those 2 numbers. It's 133. The Euler-Toyschian function of that is P minus 1 times Q minus 1, or 6 times 18, so 108. I choose a number E that's relatively prime or coprime to phi of n. And what we do is basically say, let's say E is 2. What's the greatest common divisor of E and 108? That's 2. It's not relatively prime. There's a divisor bigger than 1. E of 3, relatively prime? No. 4, no. E of 5, the greatest common divisor is 1. So yes, so that's a good encryption key. And we actually pick encryption keys that are small to make life easier. Now find a D such as D times E mod phi of n is 1. We can rewrite this as D equals 1 plus K times phi of n divided by E. Does that make sense? Sure. The mod always pulls out this part. So we just do that and we just work through the values of K until we find a solution. It takes some time. Can take a lot of time. But that's what computers are for. So here, we finally got to one where we found an integer value. So K equals 3, the D is 65. So E of 5, D of 65 gives us a solution. So why does that work? What am I trying to say here? Well, P to the E times D mod n, when we do this arithmetic, given the way it works, this is because D and E satisfy this property, this is equivalent to P to the first. because E times D mod the Toyson function is 1, P to the D E mod N is P to the 1 mod N. Again, don't worry about the math, just understand it's there. So encryption, we do this, decryption, we do this. And because of symmetry, modular arithmetic, encryption, decryption are mutual inverses. Okay. And I can decrypt first and then encrypt. I can encrypt first and decrypt. But the important thing to understand is we have this ability. We have this, oh boy, I got phones ringing on both ends. I have this ability to take a plain text value, a very large 512-bit plain text. Well, what is that? You know, that's 64 characters. 1024-bit would be 128 characters, and encrypt it all together and get another 128, 512-bit, another 64 characters that look very different. And somebody has to decrypt in this 64-character chunk. So for my example here, I'm going to use the message 6. Very simple message, 6. So 6 to the 5 mod 133 is what I wanted. N is my public key, 133. E, the encryption, the secret key, the 65 to decrypt. Well, 6 to the 5 mod 133, 6 to the 5th is 7,776 mod 133. Do the math. That's a 62. Decryption, 6. I'm going to expand this a little, just show you how the computers actually do it. 62 to the 65th. Let's bring it down to an even number, so a power of 2. So 62 times 62 to the 64th. Well, 62 to the 64th is 62 squared raised to the 32nd power. And I could keep going down like that. You know, b to the m is b to the n times m. So I can calculate 62 squared, which is 3844 mod 133. You know, so that would be a 120 to the 32nd. So this is easier to do than 62 65th because it's a smaller number. I can keep working my way down doing the math this way. I could break this 120 to the 32nd as powers of, 16. So this is really something to the 16 times something to 16. Anyway, the reason I'm showing this is, or it's 120 to 16 times 120 to 16. That's how we actually do this with the computers. Again, don't worry about doing the math. I'm just letting you know it's there. So, which then becomes, 36 to the 16, then 99 to the 8th, et cetera, boom. Eventually, we do the calculation, it becomes a 6. So the math works. That's what you need to know. Trust me. What people, and like I said, elliptic curve cryptography is even harder. What people need to understand is what's important here is E, D, and N being P and Q. I want to keep P and Q secret, but I can make N public. I want to keep D secret, but I can make E public. So I make E and N public, set them out there, and then I can do things with it. Now, how strong is it? Okay, I was a little off. 512-bit RSA is equivalent to 64-bit symmetric key strength. 768-bit RSA is equivalent to 89-bit symmetric key. So they say use at least 1024-bit. Actually, I hear currently people saying use 2048. We may even want to go further than that because there are ways of attacking this if you use a strong quantum computer. We don't have strong quantum computers yet, but we might. Okay, so let's look at the secret key versus public key. Secret key uses 1 key, public key 2. Key sizes in secret key is generally 56 to 112 like in DS, or 128 to 256 for AES. Public key is unlimited, no less than 256, usually much bigger. Secret key must be kept secret. Public key, 1 key must be kept secret, the other one is public. Secret key is really our cryptographic workhorse. We use it for secrecy and integrity of data, from single characters to blocks of data, messages and files. Public key is normally used for key exchange and authentication and signing. I will talk about those next. Key distribution must be out of band, which means we have to do it secretly outside our normal communication some way. Public key, we can use it publicly. Secret key is fast, public key is slow. Up to 1,000, 10 times 1,000 times slower. One reason the government says to use elliptic curve. Elliptic curve is not as slow for the same cryptographic strength as RSA, but still slower than, say, DES or AES. All right, so how does this work? This is the part you need to understand. Alice and Bob want to talk. They want to establish a secret encryption key that only they know, but they don't want to use Diffie-Hellman. The reason they don't want to use Diffie-Hellman is they want to trust that they're talking to who they think they're talking to. So Alice calls up Bob. Up in this picture was Amy and Bill, but anyway, let's pretend it's Alice and Bob, A and B, right? Hey, Bob, send me your public key. Bob replies, here's my public key. Alice responds, thanks. I now have generated a symmetric key, a secret key for us to use in our communication. I will encrypt it with your public key and send it to you. You're the only person in the world who can decrypt that message, even though everybody knows how to send you a secret message using your public key. You're the only one who can read it. So Alice creates this random secret key, sends it to Bob. Bob decrypts it. They now share a secret, and they can use that secret to send messages using symmetric key, using DES or AES, which is much faster. We call this a session key. So for that communication session, they've created a shared secret somehow, and they communicated with each other. So that's what we want to do. We use the public key to help authenticate and send, we'll talk about authentication in a second, but secretly share information to set up a session key. And then we use the session key for subsequent communication. The next time they talk, they create a new secret key. So I don't have to manage all these secret keys with everybody I want to talk with all the time. Every time I go to a website, I create a session key, a secure website. I create a session key in communication using AES or DES with that website for that short period of time. And it doesn't have to be AES or DS. I'm using those examples. There's Blowfish, Twofish, a whole bunch of other symmetric key algorithms out there. And the website and your browser, web server and browser communicate and decide which one to use. But we generate a shared secret somehow. This is one way of doing it. The one way of just sending one person, creating the shared secret and sending it to the other secretly. Now, what could go wrong here? We got an attacker. We got Darth here. Or evil Igor. Maybe this is Igor. They're the intruder. Alice sends a message out. Hey, Bill or Bob, give me your public key. Igor captures that message, sends it to Bob and says, hey, Bob, I'm Alice. Send me your secret key. But he pretends to be Alice. It's all electronic. Bob doesn't know the difference. Sends back public key to Igor saying, hey, here you go. Igor, who's pretending to be Alice. Here you go, Alice. Here's my public key. Igor takes it and says, thank you. I'm going to hold on to that. I'm going to take a different public key and send it to Alice. Alice sees it, thinks it's coming from Bob, creates this secret key, sends it to Igor. Igor reads this message because Alice secretly sent it actually to Igor. Igor could pass that same secret key on to Bob. So Bob and Alice could be using the same secret key, or Igor could create a different secret key to send to Bob. But in either way, this is the man in the middle. Igor has intercepted this communication, tricked them into sending him the secret. Same thing can happen with the Diffie-Hellman key exchange. Igor can intercept Alice's public key, keep it for himself, send a different one to Bob, get Bob's public key back, generate a secret shared key between Igor and Bob, a secret shared key between Alice and Bob, And Igor could intercept all communications from Alice, decrypt it, read it, send it back to Bob, modify it, create new messages, all this because Igor has these shared secrets. Why? Because we have yet to authenticate who is sending these messages. How do we know this message really came from Bob? How do we know this is really Bob's public key? Whether it's in the Diffie-Hellman key exchange where Bob created this value Y to send to Alice, how do we know it was Bob sending that? Or in the public key framework, the RSA one, Bob sends, hey, here's my public key, here's my N and my E. How do we know those are really Bob's? We still have a problem. We thought we solved the problem. We got partway there. We came up with a way of doing things secretly, but we don't know who we're doing them secretly with. So that's the next thing we have to deal with. So man-in-the-middle attacks, you get somebody intercepting these messages, modifying or reading them or copying or whatever in a way that the person in the middle can pretend to be one of the other two parties, Alice or Bob. So just thinking about that for a second, that is where we have some issues. We need to fix that problem. But we can do it with public keys if we do it right. So, and again, the names keep changing on these. Don't worry so much about it. Bob and Alice think they share a secret, but instead Bob and Darth or Igor share the secret key. Actually, I'm going to change that because I've been saying Igor. Where's my? I was saying Igor. Okay, Bob and Igor share a secret key. Alice and Igor share a secret key. All future communication between Bob and Alice compromised. Alice could send an encryption message. So I'm encrypting with the key K2 that Alice had, but Igor intercepts the message and decrypts it to recover the original. Igor then encrypts it with the message to send to Bob. In the first case, Igor may simply want to eavesdrop. In the second case, Igor wants to modify the message. So, Igor could send the original message from Alice or could send a modified message. Bob's not going to know the difference. Bob receives this secretly because it was using this encryption of this K1, this secret key that Bob had agreed to with Igor on this exchange. Had agreed to with Igor on this exchange here. Okay, this is the type of thing cybersecurity people have to deal with. We think we came up with a good solution, but a small tweak to it, a small change in the environment, and everything's broken. We have to assume the adversary has certain powers. Now, not superpowers. They don't own the world. They can't magically create and destroy everything. They can't decrypt 1028-bit, 1024-bit keys, but they can intercept messages and replay messages. And just having that power alone to intercept messages and generate messages and replay messages, they can attack. That's a little too easy because on the internet, that can happen anytime. This key exchange protocol is vulnerable to such an attack because it doesn't authenticate the participant, doesn't prove to Bob that he's talking to Alice, doesn't prove to Alice she's talking to Bob. We need a way to fix that. We will get to that, but I just want to let you know that's there. Okay, susceptible and man-in-the-middle attacks. Now, normally that's where I end the lecture because this is normally from a 50-minute lecture, but I'm going to move on. So what could go wrong? That's a small aside here because this becomes important for how we're going to deal with this. If I'm sending messages over any communication channel, there's a chance there's an error in the message. Maybe a bit was flipped. A 1 became a 0, 0 became a 1. A part of the message was deleted or corrupted. This happens all the time. You hear some static. That's error. That's a corruption of message. You see a little blip on a video. That's an error in the message. If we want to do secure communication, We can use encryption to protect against eavesdropping. We encrypt the message and send it. But does that protect against modification of the data or even falsification of the data? So I talked about, hey, for keeping it a secret, we have a way of generating the secret key and sending the secret messages. We can use symmetric key, private key messages. We can use public key. But with important data, I need to determine the data is complete and intact. Now, error detecting codes are a way of doing that. They not only detect errors, but falsification. They come under many names, hash codes you'll hear, message digest, checksums, integrity checks, or just error detection and correction codes, redundancy tests. I mentioned earlier in the class, we have that parity bit. The ones and zeros in a binary number. You've got 8 bits, the first 7 are the number, the last is a parity bit. And if it's an even parity, it's set to a 1 to make sure there's an even number of ones. Odd parity, it's set to 1 to make sure there's an odd number of ones. It's a way of checking if one of those bits had accidentally changed. There are much more complex ones out there that can do more than that. But the basic purpose, demonstrate a block of data has or has not been modified. Let me fix that. Some error detecting codes signal that content has changed. It said, hey, we found an error, but less solid at demonstrating no modification. So they're good at saying, hey, something changed, but not good at saying it's absolutely perfect. Like the parity bit, if 2 bits flipped, you don't detect it. All right, anyway. So the error detecting codes, they demonstrate a block of data has been modified. Simple error detecting codes, we can use a hash code. We can actually do parity, CRC, a cyclic redundancy check, or we can go further to a hash code. I'll come back to that in a section. Cryptographic error detecting use what we call one-way hash functions, cryptographic checksums, digital signatures. So they use cryptography to help with this. Now, why would you need cryptography to help with this? One issue is I have to know when I'm receiving the message, what is the error checking? Is it a parity bit? Is it an extra value added at the end of the message that I use? I take the whole message, calculate this hash or this CRC check or whatever the checksum, whatever they call it. And I compare it with the value I receive and see if they match. Well, I have to know the algorithm that does this calculation. If there's no cryptographic protection on the message, I just change the hash to match my changed message. I change the message, I change the checksum, it's now good. So cryptography protects us from doing that, and I'll explain how in a minute. So let's say Bob writes a letter, sends it to Alice. Here's an example of a checksum on a letter. He carefully counts the letters in the document, the number of characters. Uses them actually as converts them to numbers. So A is a 1, B is a 2, etc. Up to 26 for Z. Adds up the numbers of those letters. So like meet you at 5, adds up those, the total is 167. Sending the letter to Alice. When, oops, Amy received it, should have been Alice. She does some computation, compares her result to the one written at the bottom or at the end of the message. There's 3 options here. The counts don't match, there is no count, or the counts match. If the counts do not match, Alice says something went wrong with the message, resend it. If there's no count, Alice could say, wait, I expected a count. There's something wrong. Resend it. If they match, Alice says, hey, that's the message. I'll meet Bob at 5. But even if the counts match, it doesn't mean the letter has not been altered. If they don't match, we know it's been altered. If they do match, we're not positive it has not been altered. So, look at meet you at 5 versus meet you at 9. The difference is here in these last 4 characters. FIVE versus NINE, and they add up to the same. So the results are the same. This is a very simple code. And because it's such a simple code, it's easy to have what we call a collision, have two things that result in the same answer. You know, why? Because this code is a many-to-one function. We have many, many different ways of getting the same answer. Okay. So the simple error detecting, we can detect if a change has been made, not sure if it has not been made. And we want to make it stronger because, like I said here, Eve changed the message to 9 and passed it on. The checksum was the same. Even if Bob called up Alice on a completely different phone line and said, I sent you a message, the checksum is 167. Alice would get this and show up 4 hours late, and Bob would be really upset. All right. Let's do this stronger. So a hash function is a mathematical function that takes a large amount of data and computes a smaller number based on that data. Okay. It computes, so it may take, megabytes and megabytes of a file and create a 128-bit value. So it always creates a fixed size, 128, 156, 192 bits, whatever. And typically the message is padded, so it's a multiple of some size. Maybe it's a multiple of 1024 bits or 1K. The padding will include the value of the length of the original message as part of the padding, so we know what it is. Okay. The length field is an extra security measure to increase the difficulty for the attacker to produce an alternate message with the same hash to create a collision, because now not only do they have to have the same message, has to be the same length. All right. So we have the message or data block. We have a padding. We have the length. This is L bits plus padding plus the number L. We get the full length. We run it through the hash function. We get the hash value. The whole idea of a hash function is to create what we call a fingerprint of a file, a message or other block of data. So the hash can be applied to a single block of data or multiple blocks of data, collection of blocks of data of any size, because it always produces the same size output. Relatively easy to compute for any given number X or any input X, any data file, making both hardware and software implementations practical. That's the goal of hash functions. For any given resulting hash, any fingerprint value, this resulting value H, we call that a hash. It is computationally infeasible to find another number X such that the hash function applied to that X or another data file that results in the same hash. If this is true, it's called a one-way hash function because it's easy to go one way, H of X to create H, but hard to take this H and go back to get the X. That's what we want with our hash functions. And we want there to be very few collisions. So, if it's 128 bits, that's 2 to the 128 possible hashes. The odds of, that's a really, really big number. It's really unlikely you're going to randomly find two numbers that have the same hash. We want for any given block X, be computationally infeasible to find another Y that matches it exactly. So we can't reverse it. We can't come up with another block that matches it. We also want to make sure the birthday paradox problem, we don't want to even make sure we want to make sure it's computationally infeasible just to find any pair of numbers that match the same hash. So this one's a weak collision resistant. This one's a strong collision resistant. Very, very, very unlikely I should say computationally infeasible, and computationally infeasible with respect to a nation state and multiple supercomputers to be able to find these numbers. So there are multiple publicly defined hash functions out there. MD5, SHA-2 are some of the common ones. MD5, I'll talk about these later, but so let's look at this one. The quick brown fox jumps over the lazy dog. If I generate a hash with this, I get an MD5 value. And so there's MD is message digest. 5 was the fifth version of this. SHA stands for secure hash algorithm. This is the second version of that. Notice this SHA-2 is longer. Now notice these are also hex values. It just makes it easier again to show the hex values. The MD5 is here, the SHA-2 is here. Look at the difference between these two. I had a dog jumping over a dog instead of a fox jumping over a dog. So all I did is change those 3 letters. The hashes are completely different. Here I just got rid of the space. The hashes are completely different. Okay, they generate a unique value for every message, no matter how similar the messages are. Now, modern hash functions meet 2 criteria. They are one-way functions, which I mentioned, convert input to a digest and feasible to revert. They do not have obvious collisions, so they're at least weak collision resistant, if not strong collision resistance. Famous cryptographic ones, MD4, MD5, SHA-1, 2, and 3. MD4, developed by Ron Rivest. Oh, that name's familiar. He was RSA. Yeah, he's done a lot of crypto stuff. It's 128-bit message digest, severely compromised, never used anymore. Found the problem, created MD5 to replace it. However, MD5 is not strong collision resistant, and collisions can be found in seconds using a modern home computer. People still use MD5. They use MD5 because MD5 is good for making sure there's no accidental errors. So if I want to download a program from a web repository somewhere, often they'll have the MD5 hash for that value. So I check, make sure what I downloaded made it to my computer is exactly the same as what they said it was. And I'll show you how to do this next lecture. So it's still being used. It is not cryptographically strong. It should not be used for secrets. It should not even be used to make sure somebody didn't deliberately modify something. SHA, or Secure Hash Algorithm, developed by the National Institute of Standards and Technology, published as a Federal Information Processing Standard, FIPS 180 in 1993. Revised 95 as SHA-1 to produce a 160-bit hash. Version 2 in 2002 added 3 additional versions of SHA. SHA-256, SHA-384, SHA-512. Those represent the sizes of the hashes. So SHA-256 creates a 256-bit hash, 384 a 384-bit hash, 512 a 512-bit hash. Collectively, these are known as SHA-2. Same basic structure SHA-1, but greater security. In 2012, NIST standardized a new function, different than SHA-1 or 2, completely different, but they kept the same name. It's a SHA-3, and it's now available as an alternative to SHA-2. And if we look at this, so your message size, these actually had maximum message sizes, 2 to the 64 bits, 2 to the 128 bits. SHA-3 is unlimited. SHA-3 has either 256-bit or 512-bit hashes, like SHA-2 had multiple sizes of hashes. SHA-1 was always 190 bits, or 160 bits, excuse me. So we can look at the message digest size over on the right here. They use multiple rounds of going through these messages to calculate things. So this shows the number of rounds. SHA-3 is much less rounds, but just more complex. The block sizes, these use 512-bit blocks as input. This use 1024-bit blocks. These use something a little weird. But you don't always have to be a power of 2. MD5, SHA-1 are no longer considered secure. SHA-2 and SHA-3. Oh, 2000. I had 2012. I got to check that. Anyway, they're considered more secure. Okay. So what do we do with this? I'm looking at the amount of time I have left. I've got a way now of saying this comes from this message. I can use that to authenticate the message. I want to show that the message actually was created by me and sent to you, or created by you and sent to me. So we want to verify not only the contents of the message has not been altered, but that the source is authentic. You know, like I said, if I encrypt the message with my private key, so say I wanted to, let's say this, I want to create public key cryptography. I want to use public key cryptography. You all have my public key. I want to create a message and send it to you, and you want to know it comes from me. You all have my public key. I can send one message and everybody could decrypt it. Theoretically, I'm the only person in the world who could have encrypted that message. Because theoretically, I'm the only person in the world who could have encrypted this message, it must have come from me. That's a type of digital signature. The problem we have with this is public key cryptography is slow. If I spend my time encrypting a huge document, it's going to take a long time for me to encrypt it and for you to decrypt it. The solution to this, because everybody can read the message, I'm not trying to keep it secret. Everybody can read this document. I'm not trying to keep it secret. I'm just trying to sign and say it came from me. I'll create a hash of that message and I'll sign just the hash. Now I'm signing 512 bits. I'm not signing megabytes of data. And so I take that 512 bits, encrypt it with my public key, my private key of the public key pair, send it out there. Everybody can decrypt it and say, yep, that came from Jim. If you know that's my public key, you use my public key to decrypt it. You then compare that hash with the hash you calculate yourself of the message. You say they're identical. You know it came from me. Only a problem is somebody can create a message with the same hash. So if we have a strong hash function, this doesn't happen. If you don't want to check the signature, you can still read the message because you have it. It's unencrypted. You got the original message. You've got it. You can run a hash on it and check that I generated it or not. And so people will do this with MD5 because MD5 is not necessarily secure, but they'll say it's secure enough for what I want. And they'll sign it so you know it came. They created the same hash. There's a chance somebody created another file with the exact same hash, but unlikely. So that's what we want to do. That's what digital signatures do for us. So I'm going to talk about those next time, how they work, and then I'm going to show you some examples of how we're going to use them. Any questions on that? Okay, I know I have a couple minutes, but I think I'll just stop there because that's a good breaking point. All right, hopefully class will be in person on Thursday. I will post a message if it's not. We'll see what my COVID test says. Now, although I was vaccinated, although, and I wear a mask in class, because I'm talking, they say I'm pushing a lot of air against that mask. I'm more likely to share any germs I have. And that's one reason the doctor said I needed to do it this way. So, all right, I will see you all Thursday.
Thank you.